I'll start out by answering a couple of questions that we can pose as a way of getting started. What is geologic carbon sequestration? Basically, it's pumping compressed supercritical CO2 into the subsurface, into rock formations that we think can hold it. The CO2 has to be captured from what are called large stationary sources like power plants and natural gas production facilities. And to show you sort of what kinds of options there are, here's a diagram here. This comes from the U.S. Geological Survey's webpage. This is supposed to be a power plant. Here's a pipeline taking CO2 from the power plant to a place where the geology underneath the surface is appropriate. And there's three different things that are illustrated here. In one case, the CO2 is pumped down into some kind of geologic formation down here, normally containing saline water. And that's just to hide the CO2 and keep it away from the atmosphere. In another case, it's pumped into a hydrocarbon reservoir, a petroleum reservoir, and the idea here is to enhance the oil recovery and push the oil toward the extraction wells. In another case here, it's pumped into a deep coal seam. There's a tendency for coal to adsorb CO2 and release methane, and so you can potentially release methane for natural gas by pumping CO2 into that. So one can just sequester the CO2, or one can use it to enhance petroleum recovery. Another option is shown out here where CO2, actually natural gas is being extracted from a layer in the subsurface, and then natural gas usually comes up mixed with water and carbon dioxide. In order to sell that natural gas, you have to separate the CO2 from it. You have to then do something with the CO2, and so one can contemporaneously pump it back into the subsurface. Now, how important is this for global warming? Bernd showed a slide that's similar to this. This comes from the IPCC report. This is the amount of carbon dioxide released globally to the atmosphere per year. This shows projections of how it might change over the next century. And also, depending on what trajectory you take, it shows roughly what the amount of global warming that's projected from the climate models is. So if you look at what you can do with conservation and energy efficiency, renewables, which we're working very hard on here, but this is the sort of projected wedge that you get from them. Nuclear, if we expand it by quite a bit, could make this much. If you switch from burning coal to burning gas, you can get a little. And then carbon capture and sequestration is actually the biggest single chunk. And you could potentially get 10 to 20 gigatons per year stored. So what we're talking about here, the total volume of this wedge is something like 1,000 gigatons of CO2, and we'll keep that number in mind when we talk about the size of the experiments that are being done today. And you can imagine this sort of shows ramping up from being a significant amount in, say, 2020 up to 10 or 15 gigatons per year by the late part of the century. This, by the way, this is moved, I guess I moved the diagram. This is supposed to be plotted at 2010. We're about at 30,000 at 2010. We're slightly above the highest curve on here at the moment. So where will the CO2 be captured? This idea of large stationary sources is to distinguish them from things like automobiles and other parts of the transportation sector. It's not really possible to capture CO2 from cars. That's one of the reasons we're thinking about converting to battery-powered cars. But this is a map of all of the large stationary sources in North America. There's about 4,600 of them that have been identified. You can see there's a large concentration in the eastern US. If you look at the global map, the similar large concentrations are almost entirely in Europe and in eastern China. Another way to look at the need for carbon sequestration is that it seems an inescapable fact that coal and natural gas will continue to be used for electric power for some time into the future. This shows the division in the US, how much of the CO2 that's produced in energy production, or how much of the CO2 produced from stationary sources goes into comes from electricity generation as opposed to other sources. And you can see that electricity generation is most of it. And then if you look at the projections from the Energy Information Agency over the next well, the 25 years between 2005 and 2030, you can see that renewables, and, which are in the light blue, are expected to double over this time period, but the emissions from oil, gas, and coal are also expected to double. So even though renewables will be increasingly important, considering the population increases and the increases in everyone's standard of living across the world, there's going to be a lot more coal and gas also burned. Okay, so where can we put the CO2? As Bernd mentioned, the best idea that anyone's come up with is in geological formations. They have the requisite scale. They're quite large, and they're relatively accessible. They're only a couple of kilometers below the surface. This is a world map of likely places that CO2 could be sequestered. It's basically a map of what are called sedimentary basins. The best ones are showed in the darkest colors. The intermediate colors are possibilities, and the light colors are the types of rocks that you couldn't sequester CO2 in. They're broken into 3 different types: oil and gas fields. These we know a lot about because we're pumping oil and gas out of them now, and the companies that do that have characterized those rock formations quite a bit. There's something called unminable coal seams, which is kind of a difficult term to define. You can see that this number up here, the difference between the lower and the upper estimate is not that large. For the other 2 numbers, the difference is very large because these rock formations are not well characterized. Even the definition of unminable is an issue. What's unminable today might not be unminable in 20 or 30 years. So if you look at that in pie shape, basically so-called saline formations make up the largest chunk of what's available for subsurface space to put CO2. So what is a deep saline formation? Well, basically it's sandstone. If you look at it in outcrop, this is a picture from northern Arizona. You've seen sandstones. This is red varieties and less colored varieties. If you look at them like a petrologist would, and this is done by cutting a thin section of a rock, you just grind it down on a microscope slide to a thickness of about 30 microns, and then you can look at the internal structures of the rock. This is a relatively coarse sandstone where the individual grains are approaching 1 millimeter in diameter, and this blue area is the pore space in between the grains. So this would be a very porous and probably very permeable sandstone. This is a thin section of another kind of sandstone which has slightly smaller grains, but also the pore space has been filled in by what we call cement and other minerals, so that there's not as much pore space available. If you have a sand that's basically minerals of all the same size, you get a lot of pore space. If you mix sand with clay, the clay fills in between the sand grains and you don't have a lot of space in it. Okay, why does it need to be deep? Well, this has to do with the properties of carbon dioxide and its phase diagram. This is a graph of depth in meters, which also can be considered to be pressure if you consider it as hydrostatic pressure, the pressure or the weight of an overlying column of water. At the surface, of course, CO2 is a gas and it takes up 22.4 liters per mole, but it turns into a supercritical fluid at a depth pressure that's a little bit less than 100 bars, and its density then goes from practically 0, like a gas, up to about 2/3 to 3/4 of the density of water. So this means that you can use a lot less space to store this CO2, and also it won't be so buoyant if you've got it compressed down to this density. What's shown over here is sort of the range of temperature versus depth that you typically find in crustal rocks. The gradient is between 15 and 30 degrees centigrade per kilometer. And what's shown on these 2 diagrams is what the difference is if the rocks are relatively cold versus relatively hot. So the best situation is that they're relatively cold, which means that CO2 will reach the highest density at the lowest pressures. Another interesting aspect of supercritical CO2 is that even though it has a density that's about 3/4 that of water, it has a viscosity that's about 1/15 that of water. So it's very runny fluid. The target storage range then is between about 1 kilometer depth, where you can make sure that it's in the supercritical stage, and about 3 kilometers depth or a little bit more. And the region that there's a bottom to this depth is that the cost of drilling increases with depth. From my experience, and I think what most other people have done, the cost of drilling increases by about like the square of the depth of the drill hole, maybe a little bit higher power. Why are the formations saline? Well, sandstone starts out by accumulating as sand on the ocean floor. This is a map of where sandstone is accumulating today. It's actually a map of the thickness of sediment on the ocean floor, and the scale ranges between 0 and 20 kilometers. Out in the middle of the ocean, like here, there's not much sand being transported. All the sand has to come from rivers draining the continents, and so the sand accumulates at the edges of the continents. The most rapid accumulation is here in the Bengal fan, which is coming from rivers that are draining the Himalaya, which are eroding very fast. Other places where there's a lot of sand being dumped in the ocean are in the Gulf Coast because of the Mississippi River and northeast of South America. So it starts out with the pore space filled with seawater. As these sediments age and evolve, usually the salinity of the water actually increases, and it ends up with several to a few tenths of a percent of salt in the end. So the rocks that we expect to be able to store CO2 in, all of this pore space is not empty, it's filled with saline water. Cap rocks and seals. So because CO2 is less dense than water, if you try to put it into a formation, it immediately tries to go up toward the surface. And so the first thing you need to do is to have your sandstone layer capped by a different layer that has a much lower permeability. And these kinds of rocks are called cap rocks or seals, and basically they're shale. Shale is a fine-grained sedimentary rock made up originally of clay minerals, and still made up mostly of clay minerals, but lithified. So as you pump CO2 into a reservoir, first it tends to rise due to its lower buoyancy, and so you hope you have a sort of ceiling on your reservoir. So it has to be trapped by this cap rock. Eventually, as things move around, it can be trapped as small bubbles in the pores due to surface tension. It also slowly dissolves in saline water. CO2 is slightly soluble in water, and it forms acetic acid, or carbonic acid, I'm sorry. And then in the long term, it can precipitate as carbonate minerals, and that would be your most long-term and permanent storage. Just for kicks, I brought a couple of pieces of rock core in here. This is a piece of sandstone that has permeability of about a tenth of a Darcy, and this is a piece of shale that has a permeability that's about 10 to the 5th times lower. So this is the difference you're looking for. You're looking for a reservoir that's made of that stuff and capped by a shale. This is not a situation that's all that difficult to find. On the other hand, when you start thinking about how small those spaces are in the sandstone and pumping billions of tons of CO2 into it, it doesn't seem like it's so trivial. So the sedimentary basins of the US that are being considered, some of them are labeled on here, the blue. This comes from the Geologic Sequestration Atlas that's put together by the DOE Fossil Energy Office. In California, we have the Central Valley. Out in the plains in the north, we have the Williston Basin. Over here in the Midwest, there's several basins, the Michigan Basin, the Illinois Basin. The Gulf Coast has very thick sections of sedimentary rocks that are compatible with this idea. The New England states and the Middle Atlantic states, most of the rocks on shore are not very good for storage, but actually there are offshore formations underneath the continental shelf that could potentially be used. Getting closer to home, there's been an assessment made of storage capacity for various rock formations in California. Most of the ones that are targets are in the Central Valley. Red here, by the way, is natural gas fields. I don't know if you know, but the northern part of the Central Valley is a large region of production of natural gas, and of course there are oil fields scattered all around the state. If we look even closer, well, let's see. If you look at a cross-section of the Central Valley, about at the latitude where we are, a little bit lower, a little bit farther south, the sediments look like this. This is close to this is the San Andreas Fault here. The Sierra Nevada are over here, and this is the Central Valley. I cut off the horizontal or the vertical scale on here, but I think it's about 20,000 feet of depth, or about 6 kilometers. And the yellow is the sandstone layers that have been identified. And of course, they're known reasonably well because of all the drilling that's been done for natural gas and oil. And then the gray areas would be shale. So the idea would be to pump CO2 into these sandstone layers, hoping that the shales above them were going to keep it down there. If you look closer to home at a particular target formation, this map you can't read very well. This is Fairfield, this is Vacaville, Concord, Walnut Creek, and Antioch here. And then this is a formation, or sandstone formation, called the McKelvey sandstone. And it's contoured in terms of depth. The depth of this sandstone is like over 10,000 feet on this side and goes up to about 3,000 feet on this end. This is part of it that's less than 1 kilometer below the surface, so wouldn't be a target for sequestration. And then at shallower levels, there are shale units that would be relied upon to hold the CO2 down. If you look in the middle part of the continent, the structure is a little bit more simple. This is, of course, a picture of the Grand Canyon. There's about 1 kilometer of sediment between the surface here on the north rim and the top of the Precambrian igneous and metamorphic rocks. There's some sandstones in the middle here that are about 350 million years old. And one of the things one has to be aware of is what environment these rocks formed in. If one is thinking about storing CO2 in places where nobody's drilled a lot, you have to know something about the sedimentary environment and how these rocks formed and what their properties might be as a consequence. These rocks are about 350 million years old here in the middle of the Grand Canyon sequence. And this is a map of North America that's been reconstructed from about 350 million years ago. And you can see that most of this part of the continent was flooded. For one reason or another, the sea level was higher relative to the average elevation of the continents, and a lot of the continent was flooded. And consequently, there's a lot of large, sort of low relief basins that were formed in that time that now contain relatively flat-lying sedimentary rocks. Another place where there's a big basin is this Williston Basin in the north-central U.S., where they've estimated in a single formation here they can store about 37 gigatons of CO2. And again, it's about the same age as the previous one, and it represents this sedimentary basin shown here. Okay, is geologic sequestration being done yet? Well, one of the reasons people think this is a likely technology to be pursued is that it is being done at a scale that's a lot smaller than it needs to be significant. This is a map of all of the projects where more or less, and sometimes intentionally and sometimes as a byproduct of other things, CO2 is being sequestered underground. The ones that are solid are actually CO2 sequestration experiments. The ones that are stars here are actually enhanced oil recovery, where the CO2 is being pumped in the ground to push oil out, but in fact a lot of the CO2 stays down there and they're effectively sequestering CO2. So now the bottom line is there's a lot of places where this is being tried and tested for various reasons. The biggest single commercial project is done by Statoil Hydro in the North Sea. This is with the location here between Norway and Scotland. They're pumping natural gas out of a formation there. Again, they're separating the CO2 and they're pumping the CO2 back into a sandstone formation that's about 1,000 meters below the bottom of the seabed. In this particular case, they're encouraged to do this by a tax that the Norwegian government put on the release of CO2, and so they're saving themselves money by injecting the CO2. This also shows the scale. When the project is done, they expect the footprint of the CO2 as it spreads out in the formation from where they inject it to be on the order of 10 or 15 kilometers wide. So the CO2 will have migrated a long distance in the subsurface. This, for instance, becomes an issue when you're trying to do that in a populated area that's not under an ocean, because people own that land at the surface, and they actually own the pore space underneath them, and if you may have to pay them to use their pore space to put the CO2 in. That may not be that hard to do. Another big project is in Algeria. Again, this is a place where they're producing natural gas, and then they're pumping CO2 down into a different part of the same reservoir. This they're also doing at the scale of about 1 megaton of CO2 per year. So if you remember from the early slide, in order to do this globally, what you want to do is sequester on the order of 10 gigatons of CO2 per year. So that's 10,000 of these 1 megaton per year CO2 sequestration experiments. This is not a small-scale idea. The major obstacles, there's a longer list than this, but this is adequate. There's a lot of policy-related questions. In addition to cost, there's regulation. Who writes the regulations and what are they going to be? The EPA has to do that for the US, and they haven't finished with that yet. Who's liable and for what? Who owns what and who's relates to the liability? And then in the end, there's also this public acceptance issue. If there's any sort of sense that there's a risk involved, and you live in an area where the CO2 is going to be stored, there's little reason for you to want to see the CO2 stored under your ranch or your house, unless perhaps you're paid enough for it. Science issues are listed here: the permanence of storage, exactly how the trapping processes work and how effective they are. Long-term effects, we can sort of see what happens in these sequestration experiments during the time they're operating, which is 10 years, 15 years. But we want to keep the CO2 down there for 100 to 1,000 years to prevent it from going into the atmosphere. And predicting what's going to happen on that time scale is a challenge still. If there are impacts on potable groundwater, these have to be detectable and dealt with. Induced seismicity is getting to be of wider interest. If you pump CO2 in, you pressurize the rocks and you can cause small earthquakes. And there's a number of other things. I won't go through them all. Okay, so I like to use this cartoon to think about what you might run into pumping CO2 into a sandstone. This is supposed to be a sandstone formation here with a shale layer on top of it that would hold the CO2 down. This is the well going down into it. Actually, some of the way that they've done it in the big experiments, they actually put horizontal wells in that sort of turn around and go through the formation horizontally so that you can pump CO2 into a larger cross-section. Anyway, as you pump the CO2 out, you're worried about the injection rate at the well. Can you actually force the CO2 into the formation? How much overpressure is necessary? Will it plug itself up at some point? Is the capping shale integral? Could be fractures through it. It could be discontinuous, and this could cause you problems. And there's a question of how well you can characterize that ahead of time. Mixing between the fluid chemistry where you've got the CO2 is going to be different than where you haven't pushed it yet. And along the boundary, there's a lot of chemistry going on. Fingering, you don't want the CO2 to go off in little fingers very far away from where you're pumping it in. You would like it to go as a sort of unified front to fill up most of the pore space close to your well and within the region where you've gotten the permit to put it. There'll be chemistry going on here, as I mentioned. Fluid minerals will be dissolving and they'll be reprecipitating to some degree, and this will change the pore structure and the permeability. You'll displace the brine. For every cubic meter of CO2 you put in there, you'll push brine out somewhere else, and you could push it upward as well as out, and that has to be dealt with. And you will overpressure it, and that may induce some seismicity, and that may be of concern to the people above you. So a lot of the research that we're doing that's sort of geologically and engineering focused is in dealing with some of these things that are aspects of CO2 sequestration and figuring out what we can do about them or whether we can quantify exactly how much of a problem they are. Quickly, I'll outline some of the things we're doing in the Earth Sciences Division. So we've got a program that I would characterize as applied sort of targeted research. The funding for this comes mostly from DOE's fossil energy program, along with EPA and a couple of other places. We also have basic research. Most recently, we've gotten this Energy Frontier Research Center funded, which involves more than our division, also Computational Research Division and MSD. And we have basic support from the Office of Basic Energy Sciences, Geosciences program. And the newer parts of this overall program have to do with biosequestration, which I'll get to, I hope, before I finish. So some of the things we're doing are illustrated here. If you want to understand what's happening in the subsurface, it's a really good idea to take part in experiments where CO2 is being pumped into the ground, and you can monitor both the fluid composition and the pressure and the distribution and flow of the CO2. And scientists in ESD have been involved in a number of projects both in the US and elsewhere. This is a picture from Australia and the project in North Africa. We're also involved with the DOE's Carbon Sequestration Partnership Program. This is the flagship program for the Fossil Energy Office. The country's been divided up into 7 regions. Each region has a substantial budget to do demonstration projects involving CO2 sequestration. The idea is the geology is quite different in different parts of the country, and there's different issues that have to be addressed. We have been the technical leads for the West Coast Partnership, which is shown in blue here. So we do some laboratory work, forcing CO2 through rocks and imaging it with sort of X-ray tomography. We do modeling of flow in the subsurface. This is a small-scale injection experiment that was done in Texas, and it's a model of where the CO2 went as they pumped it into the formation. There's reactive geochemical modeling, trying to take account of this chemistry that's going on in association with the flow. This sort of shows, imagine the well being here, the CO2 being pumped into the formation, rising toward the cap rock, and then there's an interface between the water that has dissolved some CO2 and has become acidic and the water that hasn't seen CO2 yet, and this sort of mixing zone in here has large gradients, and that's where the mineral dissolution and precipitation will be going on. We're very good. We have a number of people that are experts at making measurements in the field, both geophysical measurements and geochemical monitoring. We've got expertise on fluid sampling at depth and also in imaging density variations that are caused by the presence of CO2. Now here's an example of a simulation project that's being done by Joe and Burkholzer in our division, and it's kind of gives you an idea of what the scale would be like for a real-life situation. They've modeled the idea of storing large amounts of CO2 in a particular sandstone unit in the Illinois Basin under the states of Illinois and Indiana. This map shows the stationary sources where the CO2 would be collected. This shows the depth to the sandstone unit, which is the Mount Simon sandstone. And the next slide shows, so they've imagined that the CO2 would be injected into the subsurface in this sandstone in this region in about 20 different wells. And then as time goes on, after a half year, 5 years, 50 years, you continuously inject for 50 years. This shows how pressure builds up in the Mount Simon sandstone and how big the footprint of this pressure increase is. So if you stop injecting after 50 years, things still keep moving outward because you've overpressured this central region. And there's a number of issues that this raises. For instance, if you have different companies pumping CO2 in these different wells, eventually their CO2 starts overlapping with other people's CO2. And then it becomes an issue as to who owns it and who's responsible for it. But at any rate, you can see that it affects, in the end, a region that's the size of the entire 2 states. Another interesting thing that was done in our division by Don Vasco is using satellite radar interferometry data to monitor the CO2 injections in northern Algeria. This is a desert area with no vegetation, so you can see uplift of the surface very clearly. The blue shows the uplift rate in millimeters per year. Red is where the injection wells are, and you can see that it can detect the uplift due to the injection of CO2 at depth. There's a lot of interest in this approach to monitoring. The scale is from -5 to +5 millimeters per year. Okay, so again, quickly, The sort of basic science that we're doing with the EFRC has to do with these small-scale processes that take place in the pore space in the rocks and the interaction between the CO2 fluid, the saline brines that are in there to begin with, and both of them and the minerals. And this goes from the field scale, which eventually you have to make predictions at, down to the molecular scale where of course, all chemistry happens at interfaces at the molecular scale. And in the end, one has to understand how these things work at that scale in order to make predictions at larger scales. And this brings in a lot of the capabilities that we have for doing molecular and nanoscale characterization, fabrication, and modeling. We use the EFRC itself uses virtually all the large facilities that we have here, including the biology facilities, because we're interested in how microbes may intervene in the chemistry in the subsurface. We've also got Oak Ridge involved because their neutron science facilities are very useful for studying structure of water in confined spaces and changes in the properties of materials in that kind of scale. We have Livermore involved because they have some analytical capabilities that are good at the nanoscale. And I won't go into this in much detail at all, but the research thrust areas are listed here, and you can imagine something about what they are. Controlling carbonate mineral nucleation and growth, so understanding this sort of long-term stage of sequestration that might turn CO2 into carbonate minerals, and whether or not we can control that. And even though we might not be able to store a lot of CO2 as carbonate minerals, one thing we might be able to do is help the cap rocks. The cap rocks, for instance, if they have leaks in them, if we could use carbonate precipitation to make them self-sealing, for instance, this might be a very important aspect of convincing people that you're going to keep the CO2 underground. I mentioned before the structure dynamics and transport in nanopores and thin films. And then there's this issue of emergent processes, how these small-scale, this is a molecular dynamics simulation of sodium chloride brine up against supercritical CO2. And then finally, there's this issue of pushing a low viscosity fluid into a high viscosity fluid. And depending on the rates at which you do that and the pore structure, this could either be a very simple process or it could be very complex interfingering geometry. Okay, so in terms of how this CO2 sequestration links with other things that we're doing, advanced computations come into play in a number of areas. Certainly it overlaps with the carbon capture technology and combustion. Climate modeling and energy analysis give us a framework for the value of this work. Biofuels and genomics research are important. For instance, certain biofuels, if you burn them, the CO2 that will come out from that will have different sort of trace constituents in it than burning coal and natural gas. The advanced analytical capabilities, as I just mentioned, are going to be all used, basically. And of course, I say this with a smile, we can always use improved laboratory facilities, which is one of the things we want to do in the future. Okay, I'm going to finish up with a couple of slides here on carbon cycle 1.0, the actual carbon cycle. So one of the things that's a theme of the biosequestration work is sort of taking care of the Earth's natural carbon sequestration processes. Overall, the anthropogenic emissions of CO2 into the atmosphere in terms of carbon is about 7 gigatons per year. You have to multiply that number by whatever it is, 44 divided by 12 in order to get CO2 in gigatons per year. Natural processes sequester about half of it. So some of it goes, about half of that goes into the oceans. As you increase the CO2 concentration of the atmosphere, a lot of it goes into the ocean and eventually gets sequestered by sedimentation on the ocean floor. But terrestrial ecosystems also take up about the other half of this 3.5 gigatons of carbon per year. And what we don't want to do is slow this carbon uptake down, because we were talking about what we need to do to address the overall anthropogenic problem What we want to do in the future is to be able to sequester something on the order of 3 gigatons of carbon per year. The Earth is doing that already, and we don't want the Earth to do that any slower. Okay. One place that we're particularly worried about is high-latitude permafrost soils, which store somewhere between 700 and 1,000 gigatons of carbon at the moment. And if the high latitudes warm, there's a possibility that as these permafrost areas defrost, there'll be a release of both CO2 and methane. And one of the issues is that it's very uncertain how big this effect will be. In a recent paper, the various scenarios for how much atmospheric CO2 increase there could be by defrosting the permafrost areas varies by a large factor, and this is because we don't understand fully exactly how these systems work. So this is an area that deserves some further research. In general, all ecosystem models for how carbon goes from being captured by photosynthesis to being stored in soils are all still pretty crude. And there's a lot of work that needs to be done on this, both in understanding the processes and understanding even the physics of the transport in the soil, and more importantly probably the role of microbial communities in sort of moving carbon around and reconstituting it. So just in picture form, carbon capture occurs by photosynthesis. Microbes are involved in changing that carbon into other forms. And eventually, if it works well, you want to have that stuff stored as carbon, as organic matter in soils and in a stable form that will stay there for a long time. This work also takes advantage of the expertise that we have in biology and ecology. And just as a final sort of thought, I'll show you this picture that was developed by Christer Jansen and Trent Northern, which shows how you might be able to combine things and how that might work to your favor. If, for instance, you can combine carbon capture, sequestration, and biofuel production. This shows coal-fired power plant, flue gas, taking that CO2 and putting it into a pond where you're growing microalgae and making biofuel. You're getting the water from the pond by pumping saline water out of an aquifer that you're pushing CO2 in so that the pressure doesn't go up. And so we don't know whether this would work or whether it would be economical, but it seems to me that if you've got more than one way to make money out of doing this, you're more likely to want to do it. Okay. So here's just a list of current carbon cycle research that's going on, and this is an example where we're starting to get many different divisions involved in working on related projects that will hopefully in the long run help with carbon sequestration. So I'm finished there. Thank you.